We're Team Takeo Comfort Solutions, and our project is the SmartPlug Bluetooth button, transmitter, and receiver. Our technical directors who have been guiding us along the way are Phil Manning, an embedded controls engineer, along with Nick Costello, also an embedded controls engineer. Our team consists of Andrew Crawford and Kevin Kwan, the two electrical engineers, and myself, David Huang, the computer engineer. Takeo Comfort Solutions is a 100-year-old third-generation family-owned global company based in Cranston, Rhode Island. Takeo manufactures high-efficiency indoor heating, cooling, and plumbing comfort systems. My team and I have been assigned to assist the company by improving the efficiency of one of their hot water recirculation products. Hot water recirculation is a process that uses a circulator pump to ready faucets and taps with instant hot water. Cold water in the pipes is pumped through the water heater, and the circulator continuously circulates hot water through the plumbing system. In places like California, where there are water shortages, mandatory requirements are in place for on-demand hot water. As a result of waiting for running water to heat up, the average residents can waste up to 12,000 gallons of water per year. Our anticipated best outcome was to develop an improved SmartPlug that is Bluetooth enabled with the help of Nordic Semiconductor's nRF52840 Bluetooth processor, in addition to a prototype of the Smartbutton. The SmartPlug's PCB was to be modified so that it contained the nRF52840, while the Smartbutton was to have a custom PCB that was also equipped with the nRF52840 after we had two Bluetooth modules communicating properly. At the end of April, the anticipated best outcome was not met due to issues with the Smartbutton's hardware and firmware, along with issues with the SmartPlug's hardware. As a team, we accomplished several milestones that were integral to the progression of this project. We researched how Bluetooth technology worked using central and peripheral devices, wrote firmware for the SmartPlug and SmartButton to connect and interact with each other over Bluetooth, modified the SmartPlug's PCB to utilize the Adafruit nRF52840 module, and also designed a prototype of the SmartButton with a custom PCB. The economic impact of the improved SmartPlug, in addition to the SmartButton, would result in a $380,000 to $475,000 increase in annual sales of on-demand recirculation products for Takeo. The goal of our project was to improve the efficiency of the SmartPlug even further by adding a manual activation device to activate the SmartPlug with the push of a button. We worked on a physical button that can be placed next to or near sinks and showers for ease of access. Takeo Comfort Solutions SmartPlug notifies the water circulator when to begin pumping hot water. A residence's water usage pattern is monitored by the SmartPlug and is run through an algorithm that determines the most efficient times to begin the hot water recirculation process. This allows for 94% more energy efficiency by only providing hot water when it is needed. Finding the appropriate Bluetooth processor was the first challenge our group encountered. We needed to find a Bluetooth processor powerful enough to communicate through walls, have up to 150 meters line of sight, and contain enough processing power to perform instructions such as the learning algorithm. We decided to go with the nRF52840 chip from Nordic Semiconductor due to its 2.4 GHz long-range transceiver and processing power. Companies such as Adafruit have developed their own Bluetooth modules using this chip to allow easy programming and testing. We decided to utilize the Adafruit nRF52840 Express Feather because of its Arduino compatibility. To enable Bluetooth on the existing SmartPlug, we had to replace the existing processor on the SmartPlug with Nordic Semiconductor's nRF52840 that was on board the Adafruit Feather nRF52840 Express. In order to utilize the Adafruit nRF52840 Bluetooth module on the SmartPlug, research was conducted on the pinouts of the old PIC 16F1825T-ISL from Microchip Technology in addition to the Adafruit Feather pinouts to ensure a proper transition between the processors. After confirming which pins on the old processor were required for the new Nordic chip, and confirming the physical dimensions and specifications of the pads on the PCB, the old PIC was removed from the PCB and a 14-pin header adapter was soldered in its place. In addition to the 14-pin header adapter, a dip board was also installed to enable external wiring to a breadboard where the Arduino module would be seated for testing. Now I would like to introduce Andrew, who will be talking about the Smartbutton.
As David said, the Smartbutton is the device that is meant to be conveniently placed around a residence, which will remotely activate the SmartPlug. The initial specifications of this button included being powered by a coin cell battery for a 5 to 10 year battery life, about a 150 meter line of sight range, waterproof, and universal orientation. When the user is about to wash their hands or take a shower, they will press the button first, which will send a signal to the SmartPlug and begin the hot water recirculation. The electronics behind the button are similar to the modifications to the SmartPlug. Since the Adafruit Feather worked very well during testing, we decided to take the essential components from that module and put them on the PCB for the button. The main component that is transferred over is the Raytac MDBT50Q, which contains the Nordic nRF52840 Bluetooth chip. This Raytac module has the antenna, flash memory, and processor, which makes it the brains of the button circuit. On the left is a schematic for the Adafruit module. We were able to obtain this drawing from the Adafruit website, which has allowed us to determine what the button PCB design should look like. On the right is the schematic I designed based off the Adafruit drawing. The Adafruit Feather has a relatively simple design, and as you can see, some components are voided because they are not necessary for the PCB I want to design. I took all the essential components and transferred them into our new PCB for the button with the addition of a coin cell battery holder. Using Altium Designer, I drew the schematic for the circuit and created the PCB for the prototype. The prototype is a 2x2 inch 4-layer board that takes up to 3.3 volts either from a lithium battery or from a DC power supply in case we need to troubleshoot. Jumpers are used to disconnect the battery in case there are issues with that specific power source. If we are trying to test the battery, we would use the coin cell holder located on the bottom of the board. Although this is a simple design, many of the routes between pads overlapped. Therefore, David and I routed top and bottom layer traces with vias. Here you can see one of the two PCBs I have assembled for the button. On the left side of the board, there are two 4x1 headers, which are analog and digital pins used for troubleshooting. Under those is a 2x5 pin header called the SWD debugger, which I will talk about more in the next slide. On the bottom right of the board are three 2x1 headers. The one called 3.3 is the direct power supply, and the other two are the jumpers, which are disconnecting the battery holder, which is shown on the right. The last few significant components this board contains are the two buttons, one for reset and one for the main button push function, a red LED for troubleshooting, a blue LED to display connection status. There's a micro USB port for ease of programming, and of course, the main Raytac module. The reason I assembled two PCBs for the button is because some of the components on the first version may have been damaged. The first version of the PCB passed a continuity test using a multimeter on 3.3 to ground and several other pins, but the board still malfunctioned. It initially took in almost a full amp when connected to the DC power supply. That is enough current to guarantee damage to the board and its components. I can normally spot shorts on simple PCBs such as this one. However, it is impossible to tell whether or not there was one under the Raytac chip. As you can see on the right, the Raytac chip is smaller than a quarter, and the pins are tiny and very close together, which requires extreme patience and precision if soldering by hand. I used a stencil with solder paste for this board, which I believe caused the problem. The stencil let too much solder paste get on the pads, and placing such a small component without even seeing the pins or pads may have spread the paste to areas it shouldn't be.
Hello, my name is Kevin Kwan, and I will be discussing the code that was implemented for this project. A large part of coding for this project involved learning about a central and peripheral route, along with making use of characteristics on both sides. For the two modules to communicate with one another through Bluetooth, a characteristic and client characteristic was set up for the central and peripheral respectively. In addition to this, in order for the two modules to send data to one another, making use of a characteristic write was needed, as well as providing the necessary permissions to allow for this. Another important function for this project was the bounce function for the button. This was to ensure that the button knew a button press was indeed pressed. The debounce function is a simple but necessary part of the button. Now, moving on to some of the results from our testing of the BLE aspects of the modules. Making use of the built-in user switch as well as the built-in LED, we were able to test whether the BLE connection was secure, in addition to whether the debounce function and the characteristic write were functioning properly. The two solid blue lights shown indicate a BLE connection, and the red LED indicates a button press. As for checking if the data is being sent, we look to the serial monitors of the two modules. From them, we can confirm that a connection is made, along with when the button is pressed, a characteristic write is performed on the other side. With the conclusion of our presentation, the team would like to give a final thank you to our technical directors, Phil Manning, Nick Costello, and Mike Smith, as well as to our capstone director, Dr. Sunak. Thank you.